Welcome to Troubleshooting 101. This is a course that's going to attempt to teach you how to make some basic electronic repairs. Maybe a good place to start is to build a meter that would allow us to do some of this troubleshooting. So as part of this course, we've asked you to purchase a digital multimeter kit from Elenco, model M2666K. This is a wide-range digital multimeter, but it also has a capacitance meter and also has some features for transistor testing. The manual that's included with this video is a PDF of the paper copy that's included with your kit. The PDF file numbers the first page as page 1, but in the paper copy, page 1 will be the back. So the page numbers you see here in this video are going to be off by 1 compared to the paper copy. Also, the kit gets revised periodically, and there are some minor changes to the manual. So the manual you may actually have in your kit might be just slightly different than the one in this video. This is what our meter is going to look like once we finish it. Let's go to the next page. The assembly of this kit is set up in 6 sections. We're going to take a look at section A in this video. It's going to be the meter display assembly, the circuitry that goes with it. What's on the following few pages is a description of the theory of how this multimeter works. We'll come back and take a look at this in a later video. But let's go to page 7 of this PDF file. Before we start to assemble, just a couple general notes about we're going to be doing this one section at a time, and when you complete a section, there'll be some testing, and then before you go on to the next section, we're going to ask that the lab supervisor sign off on your paper copy that you've completed this. There'll also be some tasks along the way we'll be asking you to do, and the lab supervisor will just be checking that you've actually done those. And this is just to make it easier for us to eventually make sure your meter works. But if you're careless about doing these things, it's going to make it very difficult to have a working meter at the end of this assembly process. Just some general comments here that whenever you're working with printed circuit boards, you really should wash your hands thoroughly with soap and water before you start and after you finish. The reason for this is that there's some very high resistance points in our circuits, and the oils and resins on your hands can cause conductivity and really cause the thing to malfunction. Take your time when you're assembling the different parts of the boards. In general, we're going to be putting parts through holes in a printed circuit board, and some of these parts actually have a polarity or a direction to them. We're familiar with batteries having plus and minus terminals, but also some parts do too. We're dealing with integrated circuits where there are quite a few number of pins, and you can put an integrated circuit in usually one of 2 ways, and we have to make sure it's in the right way. Diodes have 2 terminals, but there is a polarity or sense to them. Electrolytic capacitors, we'll talk a little bit more about shortly. Battery snap, that's we're going to connect to the 9-volt battery with, also has orientation. And lastly, the liquid crystal display does too. Now, in building this digital multimeter, we're going to use a soldering iron that's provided in the lab. And be very careful. This is at a very high temperature, maybe around 700 degrees Fahrenheit, so it can very clearly burn you and anything around you. So be very careful that you look at the iron when you pick it up and put it back. Unfortunately, when I was younger, I didn't do that and left a lasting impression on my fingers, so I still remember that accident. But please be very careful. This YouTube video, you'll find a link in the description of the video that links to another YouTube video on soldering. I would like you to take a look at this. But one of the key things you'll learn in this video is that we need to keep the tip of the iron clean. We're going to do this with what looks like a little ball of steel wool. And then once you do that, we're going to tin the tip. This is putting a little bit of solder on the tip. This will help the solder to flow when you make your connections. Whenever you're in lab, you really need to be wearing safety glasses or some kind of eye protection. When people are soldering, it would just take a flick of a hand to have that molten metal hit you somewhere, and if it was the eye, it would be maybe permanent damage. Using solder that's not lead-based, older solder was very dangerous, but what we've got is still toxic material, so please don't put the solder in your mouth at any time. And again, you want to wash your hands before and afterwards for the same reasons that this material is toxic and you don't want to ingest any of it. Again, there'll be a video to take a look at, but here's a few pictures that we just kind of say really the things you need to watch out for. We're going to put components through a printed circuit board, and we're going to flip the board over, and the part's going to fall out. So one trick is to just bend the lead a little bit, turn it over, it won't fall back out again. We'll put the iron, once it's heated up to around 700 degrees Fahrenheit, and then touch the solder to the other side of the wire. To do that, it may take a few seconds, the solder will begin to flow, and you'll get a real shiny type connection. I'm just going to remove the iron, remove the solder, and let it cool. and then just snip off the wire that's there. We don't want to touch anything, so we get rid of it. Next side of this page are a couple examples of not so good soldering. If you don't hold the iron there long enough, solder doesn't get a chance to flow. And there's also a thing called resin inside the solder that helps it stick to the metal wires. So if you see a solder connection that's got some yellowing material on it, they just didn't heat it up enough. This would be pads where we're making connections, and we need to get solder on the entire pad to make a really good connection. So not putting enough solder in this example here shows that you may not have a connection between this wire and then this wire. Putting too much solder on will give you what looks like a ball of solder. This too can cause problems, one of which is shown below here, where you put too much solder on, you actually bridge the gap between two traces on the printed circuit board, and you make a connection that you really weren't intending to, and this will cause us to get the wrong behavior out of our electronic circuit. So a lot of times when I look at people's work, this is the things I look for. Now in the course we're going to take a look at a lot of different kinds of electronic components. And the assumption in this course is that you have no background in electronics, and this may or may not be true, but it's not a bad place to start and kind of go from there. Now capacitors are one of the things we're going to take a look at in the course. We'll later look at how would you interpret what a capacitor does, but in the short term we're going to start to use these things and learn by actually putting something together. There are two types of capacitors, ones that are polarized and ones that are non-polarized. The polarized capacitor will have a plus or a minus sign somewhere on the body of the capacitor. Usually don't label both of them, but the other one will be the opposite sign. So if this is the minus sign, then this would be the plus sign. And as you insert this in a printed circuit board, you'll have to make sure that you get the correct sign in the hole. If you don't, this capacitor can actually overheat and explode if it's put in backwards. So be very careful, and we're going to ask again your lab supervisor to check your work to make sure that these things are done correctly so that we're safe when we power everything up. Electrolytic capacitors typically have the value of capacitance printed or stamped on the capacitor, so they've just got to read off the value. Non-polarized capacitors sometimes are so small, they don't put the value there, but put a code on the capacitor. Let me explain what these things mean. Here there are 3 digits in a letter, and the first digit is a placeholder. In this case it's 1. The second digit is a placeholder, and that's 0. And the third one is 10 raised to the third power, or 1,000. So that's going to be 10,000. These types of capacitors have capacitance usually, if the number is like this, greater than 1, picofarads. And so this turns out to be 10,000 picofarads. Now pico is 10 to the minus 12th, and we use a thing called engineering notation where we move powers of 10 by a factor of 3. So if we were to take 10 to the minus 12 and increase it to 10 to the minus 9th, that would be called nanofarads. And that would be 10 nanofarads in this case. You can bump the digit over 3 more places, and you would get microfarads. Micro is 10 to the minus 6th, and that would actually be 0.01 in this case. So they all mean the same thing. It's just that sometimes it's easier to say 10 nanofarads than 0.01 microfarads. It all means the same thing. The letter that's here is also important. It tells you what's called the tolerance of the component. And what this means is that the base value is 10,000 picofarads, but the actual value could be anywhere between 10% higher and 10% lower. If you multiply 10,000 picofarads by 1.1, that's your upper limit, and multiplying it by 0.9 would be your lower limit. So it's going to fall between those two. Once we get our digital multimeter assembled, we can actually measure the capacitance fairly accurately. We'll talk about the tolerances of the instrument itself a little bit later in the course. We'll be able to measure the value. But when you're building circuitry, this is going to give you a ballpark of values, but you don't know the exact value until you have something like a digital multimeter. Lastly, there's also a number with usually the word V or volts after it. The same is true for the electrolytic capacitors. Capacitor is really just 2 metal plates with an insulator between them. An insulator can be air, it can be a thing called mica, it could be a thing called Teflon. They'll have different properties. But eventually that material breaks down. In this case it would break down at 100 volts or more. What will happen is the dielectric will begin to conduct at that point. And you just get a arcing between the 2 plates and the capacitor is no longer usable. The other component that we're going to be using in this multimeter is a thing called a resistor. And using resistors that have color bands painted on them, and they either have 4 bands painted on them or 5 bands painted on them. So 2 different possibilities. 4 bands, we're going to have to orient the resistor such that the bands are basically on the left-hand side. Normally this tolerance band is actually moved over to here, but just like the capacitor, these are placeholders in the first 2 positions. So if I had a color combination here that was green, blue, and red, the green would correspond to 5, the blue would correspond to 6, and then the red would be 10 to the power 2. So that would be corresponding to 100 times this, or 5,600. Again, we could put a decimal point from here and move it over 3 places. That would correspond to a factor of 1,000. So that'd be 5.6 k ohms or kiloohms. If the fourth band here was gold, then that would be a 5% tolerance. And again, what that means is that you would take 5.6k, multiply it by 1.05, that's your upper limit, and multiply it by 0.95, and that's your lower limit. And that resistor is going to fall between that range of values. And once we have the digital multimeter, we can measure this fairly accurately and a much tighter tolerance than that 5%. For a 5-band resistor, we have one more placeholder. And what this is going to let you do is have a range of tolerances from 1% to 0.1%. But when you orient this, you have to get the tolerance band on the right-hand side. And these are the colors that can occur for those tolerance bands. Okay, so if we had, in this case, orange, white, black, black, brown, okay, what that would mean then is the orange is 3, the white is 9, and the black is 0, so that's 390. And then the multiplier here is actually 10 to the 0 or 1, and that'd be 390 ohms. If it was a 1% tolerance, if the fourth band were brown, then you multiply 390 by 1.01 and multiply it by 0.99, and you get the range of values for that resistance. So these tend to be a little higher precision resistors. What you'll see in your kit is that each section of assembly has a little plastic bag with the parts in it. So we're just going to pull that out for section A and begin to do the assembly. Before you do that, here's a little exercise to have you figure out the values of different valued resistors here by their color code. So I get to fill that out and eventually show that to your lab supervisor to make sure that you understand how to read a resistor. Okay, this is part of really any troubleshooting and be able to tell that you've got the right component in the right place. Also see that the answers are here on the bottom. Okay, well, if I get to section A, which is the assembly of the meter for our digital multimeter. Now these are put together by human beings, and it's very possible that we missed some parts. We'd like you to take that bag out that has the section A parts in it and just check off whether you have all of the appropriate parts. So as you find these things, just going to check them off. This will help you also to identify the parts, and if you're not sure about something, you can also ask again the lab supervisor to help you. So this is what a resistor looks like, a diode, different kinds of capacitors that we've got. These are disc capacitors. Mylar is really the dielectric material. They look more rectangular in shape and usually are glossy colored. These are more of a flat color, but it would depend on the manufacturer. And the electrolytic, sometimes they just call lytic because it's just too much to put the whole word there. Here's our printed circuit board as part of our digital multimeter. This is a transistor we're going to be using in this first part. And then the liquid crystal display and some of the housing that goes with that, and then a label for the multimeter. On the printed circuit board itself, there is what's called a legend. It's showing where the component needs to be inserted. So it'll show a capacitor with its name, which might be like C1 or C17. And it'll show you which side you have to insert it through. And then we're going to bend the wire and flip it over and solder it. Some of the resistors we're going to lay flat on the board and push it through this way. And some resistors, there's not enough room. We're actually going to do a little bit of a looping around. Again, electrolytic capacitors have a polarity. You got to look for the plus and minus sign. Usually only one is shown on a board. They assume that the other one is the appropriate sign. So if they show minus here, it means that this is plus. But if the board has only a plus sign, that's got to go into that hole. Transistor has a rounded back and a flat front, and the picture on the printed circuit board, the legend for it, will show the same shape. Wherever that's stamped, that's where you got to push it through. So here's some pictures of where the capacitor, looks like C4 right here, is supposed to go, and so on. Also, we'll be dealing with some connections and switches and battery connections, and so also described here. But again, read this very carefully. If you're not sure about something, just ask the lab supervisor. Then lastly, we're going to put together the liquid crystal display assembly, and it's described here, and some pictures are also shown, so please read that very carefully. Once you've completed all this, we're going to go through a series of steps to test that what you've assembled so far works. Now, we won't be screwing everything in and putting in the final positionings in the multimeter, but we're going to stop and do some initial testing. So once you do that and complete that, you're going to have to ask your lab supervisor to come over and sign off or initial in this area right here that everything works at this point. I'd like you to try to do this in your first time you come to lab. And so this is our first lesson dealing with section A of the assembly of the digital multimeter.